Derivatives of inverse trigonometric functions. Now, finding an inverse function for the trigonometric functions has a new challenge to it. The trigonometric functions are all considered functions because they pass the vertical line test, so they all fit in our category of functions. However, none of them pass the new horizontal line test. You might not have seen the horizontal line test before, and that's just the exact same thing as the vertical line test, except the line's horizontal. And if they fail the horizontal line test, these functions are not what we call one-to-one. And it makes them difficult to find inverses of because they're not one-to-one. There's not an obvious inverse function here. Simply put, if we are not careful when we take the inverse of the trigonometric functions, we'll end up with an inverse that is not a function. Okay, so when I said it was difficult to find the inverse, it might not be difficult to find the inverse, actually, but it'll be difficult to make an inverse that is a function because it doesn't pass the horizontal line test. So here's our plan. Here's what we do for functions like this. We carefully restrict the domain of the original function to some x values where the function stays one-to-one. Then we use the inverse of that section as the inverse function. This is very closely related to finding the related acute angle where we just restrict it to finding one of the answers. And I'll jump right in and show you how this works. Find the inverse functions of y equals cos x. So let me draw a little graph of y equals cos x to get you a feel for what's happening here. So if I just draw a graph here and cos x, well, we need some points here. I'll go 2 pi there. And we'll just go a little bit back there. So pi over 2, pi, 3 pi over 2, 2 pi. And I'll add a couple more to really highlight what the issue is with finding this inverse and inverse function. So here's cosine. It goes through there, 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 there. I don't need a super neat graph here, but I do need enough that we get the feel for what we're up against here. Okay, and I'm going to add the arrow on the end to make the point that this goes on forever both ways. So now when we go to do the inverse of this, what we would do is we'd exchange the roles of x and y. And so if I did the inverse of this, what I'd get is, okay, I'd have to go from -1 to 1 because the y's became x's and the x's became y. So I'd need, going this way, I'd need pi over 2, pi, etc. And I'm only going to draw that much of it because I sort of know what's coming, but I want to show you what happened. If I find this inverse, then it would start at 0, 1, and then it would go through pi over 2, 0. And if I did the whole inverse, you'd get a function that, or you'd get, not a function, you'd get a relation that looked like that and kept going like that. And you can see that this is not a function. This fails the vertical line test because the original function failed the horizontal line test. So what we're going to do is, let me get rid of that. We don't want all of that. What we want then is to restrict the domain of cosine. We're only going to look at this part of cosine right here. And what I'll do is I'll get out a highlighter here, maybe in like a pink type thing, and I'll go, okay, so we're only going to talk about cosine from there to there. That little part of cosine is the part we'll do the inverse of. Now, when you're first doing these, it's a little hard to transfer over from a function to an inverse, so I suggest actually writing the points down that you want to do the inverse of. So in this section of the graph, I've got these key points of 0, 1, pi over 2, comma 0, and pi comma -1. And those are the 3 points that are going to define my inverse function of cosine. So 0, 1, to do the inverse, we flip the x and y value. So I get 1, 0. So that's my first point that I'm going to put on my graph there, right there, 1, 0. And then pi over 2, 0 becomes 0 pi over 2. So that's this point right here. 0 comma pi over 2. And the third point on my graph was pi -1. When I do the inverse of that, I get -1 pi. So that's right there. And that's enough. Oops, not pi over 2, just pi. And that's enough to be able to draw my graph. It goes like this, through that pi over 2, and up to there. So there's inverse of y equals cos x. Sometimes called y equals cos -1 of x. And actually, we're going to come up with an even better name for it. It's going to be, we're going to find very convenient. We're going to call this arc cos of x. Okay? So there, I did the cosine one. That's the first one you see down here. Notice that the domain is -1 to 1, and the range is 0 to pi for y's. Now, I encourage you to go through that exact same process for the other 5 trigonometric ratios. That is, try and do that exact same thing for sine. Go through and draw the sine graph. Pick a domain that will keep it 1 to 1, that will keep it, that it will pass the horizontal line test and the vertical line test. Of course, it'll pass the vertical line test. And if you need a hint to the domains that are normally chosen, well, these are the ranges of the inverses, so choose those as your domain. Now, there is some openness to choice here. You say, well, you chose 0 to pi, and the reason I chose 0 to pi is because it had 0 in it. And so when we do the inverses, we like to include 0 as our sort of central point. And so I didn't go over there and choose like 2 pi to 3 pi or some other choice I could have made. And these 6 that you see here, these definitions for inverses, do that. They sort of try and center things around an original domain that has 0 in it, or now it'll be the range will have 0 in it. So I want to mention that secant and cosecant are sometimes defined differently in this. Some textbooks will choose a different domain at the start. But I really encourage you to try to do sine. First of all, sine would be the next easiest one because it's very similar. And then so draw sine, choose this range as your domain. It'll be -pi/2 to pi/2, and try and do this transfer over and do it for each one because it's really instructive to know where these inverse functions come from. So there's the 6 inverse functions with their domains and ranges. Each one can be built from the original graph. So those are inverse functions. Yes, okay. So that's not really what we're up to. Those definitions are just defining what functions we're talking about. And now we want to determine the derivative of those sine inverse functions, which is really, really difficult, except it's so darn easy. Like there's something about this situation that's really smooth, and it allows you to handle all sorts of situations. So please tune in for these 3 derivatives that I'm going to do here. So I want to find the derivative of y equals sine inverse of x. This new function right here that I've built, and the one I'm working on here is a sine inverse. So this is the one I'm going to do first, is the sine inverse one. Okay, so y equals sine inverse of x. No way to really do that without going back to the limits and so on, and that's not what we're going to do here. We're going to say, well, if y is equal to the sine inverse of x, I can move that sine inverse over to this side, and I get sine y equals x. I've just moved that inverse function over to the other side, and when you move an inverse function over to the other side of an equation, it goes back to its inverse, and the inverse of sine inverse is just sine. And so now I can do the derivative because I have implicit differentiation ready to rock and roll. I'm going to take the derivative with respect to x of both sides. So this side, okay, the derivative of sine y is cos y, but due to implicit differentiation, I've got to take the derivative of the inside called dy dx, and the derivative of x when I'm taking the derivative with respect to just 1. So I get dy by dx equals 1 over cos y, which is perfectly legitimate, I suppose. That's an answer for what dy dx is. The only problem with that is that it's got y's in it, and when we say dy dx, we really think that y is the independent variable. We really want y to be the variable of note here, and now I've got an equation that has y's in it, not x's. So I want x's to be the main variable here. So I'm going to do a little trig identity work here, and I'm going to say, well, I know that sine squared y plus cos squared y is equal to 1, so I can solve for cos of y. Cos squared y equals 1 minus sine squared y. So cos of y equals plus or minus square root 1 minus sine squared y. And so what I notice is that sine squared y right there, and I'll get my highlighter out again, that sine squared y is right up here. Sine y is x, and so I get cos of y equals plus or minus 1 minus x squared, which I can then, I'll use a different color highlighter just to show off what I'm up to here. I'm going to take that and sub it in there, and so then I get a nice dy by dx equals 1 over plus minus square root 1 minus x squared. Very nice, very nice. That happened all fairly quickly, just using implicit differentiation and a trig identity. Now, I can do a little better here because there's something that I need to explain about this situation, is that if we're looking at cos of y here, which was plus or minus. So I'm going to go back to this line here, which ended up with this plus or minus. Cos of y, we can look at whether it's positive or negative. We analyze, is this thing positive or is it negative? Maybe it's either, but maybe it's one or the other. And if I go back and notice that I'm talking about sine inverse, that's the function I'm talking about in this particular question. And what I notice is that sine inverse only goes from negative pi over 2 to pi over 2. That's the only y values we get there are negative pi over 2 to pi over 2. So if I'm only looking between negative pi over 2 and pi over 2, that is, I'm only looking between negative pi over 2 and pi over 2, I'm only going to use values for that particular function in this section here. Oops. Over here, yeah? So negative pi over 2 and pi over 2. And notice that cosine in there, due to the cast rule, is positive all of that time. So if I'm restricted to negative pi over 2 to pi over 2, which I am, because I'm using sine inverse is restricted to negative pi over 2 to pi over 2, then cosine in that section will always be positive. And so what I get out of that is, I'm going to write that down, between negative pi over 2, negative pi over 2 and pi over 2, cos y is greater than 0. Therefore, dy by dx isn't plus minus, it's actually just plus, and there's the derivative of sine inverse, 1 over the square root of 1 minus x squared. Nice. So now, they want me to do tan next. Okay, so I'm going to do the same procedure with tan. So like a lot of stuff in trig, the first time you see one of those, it's like really complicated and really hard to follow. But then it's usually very repetitive. You go to do the next one, and it's a very similar derivation. And so what happens is by the time you do 6 of them, you're like, okay, I totally get that now. I'm only going to do 3, but 3 is enough to get the feel for how this works. And this isn't a trick just for finding inverse trig derivatives. There's lots of times in trig where the moves I'm doing here are very helpful in simplifying trigonometric expressions. Okay, so going after tan. Y equals tan inverse of x. So if I'm using tan inverse, then when I move tan inverse over the other side, I get tan of y equals x. And here comes that implicit differentiation. I'm going to take the derivative of both sides with respect to x. So the derivative of tan y is secant squared y. And then the derivative of the inside is dy dx with implicit differentiation. And the derivative of x is just 1. And then I get dy by dx equals 1 over secant squared y, which again is a legitimate derivative, I suppose, but it's not expressed in terms of x. And when we say dy dx, we usually want this derivative with just x's in it, and this one has y's in it. So I've got to do some more identity work here. What I'm going to do is I'm going to again start with sine squared y plus cos squared y equals 1, because I see that I see that squared in there. And what I know about this particular identity is that it can be modified and added onto by just dividing the whole thing by cos squared y. So I'm going to divide this by cos squared y, divide this by cos squared y, and divide this by cos squared y. And what I get is tan squared y tan squared y plus 1 equals secant squared y, which is going to be handy here because look at secant squared y, and I'm going to do this highlighting thing again to show what I'm replacing. I found out that secant squared y is tan squared y plus 1, and that really, really helps here because I can go back to my pen here and go, okay, therefore dy by dx is equal to 1, not over secant squared y, but 1 plus tan squared y. And at first, that's not very helpful. In fact, it looks like I've made it worse, but then I'm going to do this substitution that comes out nicely, is that I go, okay, well, tan squared y happens to be x squared, because tan y is x there. So what I get is dy by dx equals 1 over 1 plus x squared. And that's the end of that one. I don't have to do anything else with that one because That's done. I don't have any of that plus minus stuff to deal with like I did with when I was doing sine inverse. Sine inverse, eventually you got to think through that plus minus, which is a little bit difficult. Now then, the third one I want to do is, it says tan and then secant. Okay, so I'm going to do y equals secant inverse of x. And again, these are difficult, but they are repetitive. That is my first step when I want to find the derivative of something like secant inverse, is to move the secant inverse over to the other side where it becomes its inverse, secant. Then take the derivative of both sides with respect to x. So the derivative of secant y is secant y tan y. And then dy dx, because I'm doing derivative with respect to x, and this side's 1, and then dy dx is 1 over secant y tan y, nicely, which is a mess, but I've got some help here. Secant y, I'm going to use that fancy highlighting again. Secant y is going to get replaced by x, so that's pretty nice. And then tan y, I think I have what I need here. Tan y is going to get replaced by, I've got the identity already to rock and roll here. Oh, it needs a little bit of work because tan y wasn't rearranged for over there. So I'm going to go and just take this thing and go, okay, well then tan of y is equal to plus or minus square root secant squared y minus 1. Yes. Which, if I use this for secant y, then I get tan of y is equal to plus or minus square root x squared minus 1. How nice is that? So then I get, putting that all together, dy dx equals 1 over, okay, secant y gets replaced with x. That's the yellow highlighting. And tan y, after a bunch of work up there, becomes plus or minus square root x squared minus 1. Okay? And that's a real mess with everything that's going on there. So a little thought has to be put into here about what's going to happen with this plus or minus when we're talking about the function tan inverse. Now I'm going to go up to my picture of tan inverse here. And I want you to notice, if I look at my picture of tan inverse, I can just look at this and know from its graph that this derivative is always positive. That's always increasing. So I don't need all this nonsense here. I don't need to do anything algebraically. I can just look at this and go, well, I know that dy dx has to be positive, so I need to rig this up so I know it comes out to be positive. That is, this doesn't need a plus minus anymore because we know it comes out to be positive. And then to take care of the x, to make sure it's positive, what I do is go, okay, well, I'll just call that absolute value of x. And now I've ensured that I will get the positive answers that I expect. None of this plus minus stuff that came out of there. So 3 really, really beautiful proofs there about sine inverse, tan inverse, and secant inverse. I really encourage you to pause the video and now take and see if you can follow that and do cos inverse, cotan inverse, and cosecant inverse, because their development is really, really close to the same thing. So you could, that's a good activity to really get to know and really have the knowledge here implanted in your brain. But there's another way to do the 3 trigonometric functions. There's another way to handle finding those other 3 derivatives. So using the following inverse function, inverse cofunction identities, inverse function because we're talking about inverses, and cofunction because we're going from cos to sine, cotan to tan, and cosecant to secant, we can easily see the derivatives. There's an easy way to get the derivatives. Once you have those first 3, there's an easy way to get the other 3 derivatives. That's not what I just suggested. I suggested you go through and try and do these so you know how to do them. It's nice to know. But there's a faster way to do it using these inverse function, inverse cofunction identities. And why are these identities true? Well, that's what I'll do first down here. Before I do the derivation, I just want to show you where these inverse function, inverse cofunction identities come from. So let me just say, let y equal cos inverse of x. And what I'm going to do is come up with an expression for cos inverse just by playing around with this and using some stuff I know about cofunction identities. And if you don't remember what a cofunction identity is, well, I'm going to use it in here. Maybe you'll recognize it when I use it, even though maybe you didn't know the name of it. Okay, so same trick I did above. Cos inverse moves over to the other side and becomes cos. And my cofunction identity tells me that cos of y is equal to sine of pi over 2 minus y. And that was way back from a pre-calculus, before calculus ever came along. We learned that as an identity, that cos of y is equal to sine of pi over 2 minus y. And after I've switched over to my cofunction, then I move the inverse back over. And then a little substitution here, like what often happens when you do that little let y equal trick, is this y is cos inverse. So I get pi over 2 minus cos inverse of x equals sine inverse of x. And then I can solve for cos inverse. That is, a negative cos inverse of x is equal to sine inverse of x minus pi over 2. And then I'm going to multiply through by negative 1. And I get pi over 2 minus sine inverse of x. So these cofunction identities are a lot like the cofunction identities we had with cos. That is, way back when we first learned about cofunction identities, we found out, oh, cos of y is equal to sine of pi over 2 minus y. And these are analogous to those, except with the inverse functions. That is, cos inverse of x is equal to pi over 2 minus sine inverse of x, and that's the first one on the list there. And like before, I really encourage you to try and follow that, pause the video right now and try to do that development for cotan inverse and for cosecant inverse, because it's handy to have those skills available if you happen to forget the cofunction identities. Never mind that these skills that I'm building here are ones that can come up in other questions as well. Now, what that allows us to do is, if I want to find, okay, so up here we found the derivatives of sine inverse, tan inverse, and secant inverse. I'm going to now go after the derivative of cos inverse. So here's my going after the derivative of cos inverse of x, which I could do using the methods I saw up here. Now, hopefully you stopped and did what I told you, which was to go and try and do that yourself and come up with the derivative of cos inverse. But using the inverse function, inverse cofunction identities, what I can do is then replace cos inverse with what I know cos inverse to be, which is pi over 2 minus sine inverse. And so what I get is d by dx of pi over 2 minus d by dx of sine inverse. And this is 0. And the derivative of a sine inverse, well, we already know the derivative of sine inverse. We did the derivative of sine inverse up here, and it was 1 over square root 1 minus x squared. And so therefore I get the derivative of cos inverse is negative 1 over square root 1 minus x squared. So it's just the negative of the sine one. I really encourage you to stop the video now and go, wow, that is really neat. I'm going to try and do that myself to find the derivatives of cotan inverse and cosecant inverse. That actually goes very quickly once you have those available. So there's lots of times in here to really learn about how this stuff all works together and build your algebraic skills is the big thing I wanted to say there. Okay, hopefully you've gone and done some work there. And so here's a review of what we've found. Here's the 6 inverse trigonometric derivatives: sine inverse, tan inverse, secant inverse, cos inverse, cotan inverse, cosecant inverse, and the following identities. Okay, so you really want to commit those to memory. And the nice thing is they're very repetitive. If you memorize the first column, the second column is very, very similar. It just... It changes some signs. Oh, there's a sign missing there. There's supposed to be a negative in front of that one there. And also negative in front of this one. See, all the ones are negatives. Okay. Now then, moving on. The following identities can be helpful when using a calculator to evaluate expressions involving inverses. That is, your calculator it's got a sine inverse button, a cos inverse button, and a tan inverse button. But if we happen to want to do secant inverse or cotan inverse or cosecant inverse, we don't have buttons for that. So these are called calculator conversion identities. It allows you to find, see, for instance, if you want to find secant inverse, you can use cos inverse, but you have to go 1 over x. And if you want to find cotan inverse, you have to go pi over 2 minus tan inverse. So you can always use your calculator button that you have and just convert them over. And the question is, where do these come from? So I'm going to develop that. Okay, so let me do one of them here. So I'm going to go, let y equals secant inverse x. And like I've been doing a lot, I hope this skill is really pounding home now, is that when I want to move secant inverse over, it becomes its inverse on the other side, which is just secant. And then I'm going to play around a little bit. I'm going to say, well, secant y is 1 over cos y. That's what I know the definition of secant is. And then I'm going to use my cofunction identity, that this is 1 over pi over 2 minus y. I'm going to switch over to sine there. And once I've done that, I'm going to flip both sides. And I get sine of pi over 2 minus y equals 1 over x. Bring the sign over. Pi over 2 minus y is the sine inverse of 1 over x. All of that move to flip that thing, that 1 over x, and then I'm going to solve for y. So I get negative y equals sine inverse 1 over x minus pi over 2. Multiply through by negative 1 like I did before. Oh, I got ahead of myself there. Right here, I'm going to, where'd it go? There we go. Right there is where I'm going to do my sub back in. This is pi over 2 minus secant inverse of x. Where am I getting that from? Y is secant inverse, so I sub that right in there. And now the interesting little trick where I'm using all sorts of tricks together here. Pi over 2 minus secant inverse way up here. Pi over 2 minus secant inverse is cosecant inverse right there. So what I get is cosecant inverse of x is equal to sine inverse of 1 over x. All of that work, but that's the calculator identity right there. There's the one I can use for the calculator. If I want to find the cosecant inverse, I can do the sine inverse of 1 over x. And so I've developed this one here. Unexpected that I started with secant there and got the calculator conversion identity for cosecant inverse. Weird the way that one played out. So I'll leave the other one for you to try to see if you can do this one. Secant inverse. And instead of y equals secant inverse x being your first line, you'd use cosecant inverse. And then you follow many of the same steps. But play around with that. It's good identity practice. It's good looking back and forth. And these tricks will start to become second nature after you've used them a couple of times. The cotan inverse one looks weird, so I want to do it because it plays out slightly different. I'm going to do over here, let y equals tan inverse of x, and this one plays out differently. It ends up with a pi over 2 in there, and let me show you why that happens. So I bring the tan inverse over, and I get tan y equals x, and the cofunction identity for tan is just cotan. So it's weird the way that one plays out. And so when you get that one, what you end up with is instead of going back to cotan pi over 2 minus y, you really don't have an easy one to use there. But it doesn't have to be that difficult because tan and cotan are inverse, are cofunctions of each other. Then you can just move the cotan right over. And then when I put tan inverse back in there, there's the calculator identity. So that one plays out a little different because tan and cotan are each other's cofunctions. You get a slightly different version of that with the pi over 2 in there. And there's a slightly deeper explanation of that whole thing having to do with the graphs of cotan and tan. But this is enough for now. This nicely shows why that calculator conversion identity is a little different than the others. Okay, lots of trig stuff to use there, but a lot of what you're going to do with these inverse trig functions, just things like finding derivatives. So let's jump right in and find a few derivatives. The derivative by dx of sine inverse of x squared. So we know that let's just write over here, d by dx, of sine inverse. And this is one of those things, again, in math where it's like, you can just look these things up all the time. You can always be going back and finding your derivatives by looking back at charts and so on. But your homework and everything you do is going to go a lot faster if you just take the time to memorize these things. So that's 1 over square root 1 minus x squared. We saw that development earlier. And so if I want to do the derivative of sine inverse, what I get is 1 over square root 1 minus, well, it's now x squared in the brackets. So instead of the derivative being x becoming x squared, it's x squared becoming x to the 4th. And then the derivative of the inside, chain rule is 2x, and so what I get here is 2x over square root 1 minus x to the 4th. There's our derivative this time. Let's see. Particle moves along the x-axis so that its position is given by tan inverse of square root of t. Oh, very nice. What is the velocity of the particle when t equals 16? So what I want is the velocity being the derivative with respect to t of tan inverse, and may as well get ready here for derivatives by calling the inside t to the 1/2. So again, you can look back to see what your tan inverse derivative is. It's a little simpler, 1 plus x squared. So here I'm getting 1 over 1 plus t to the 1/2 squared, not x squared, t to the 1/2 squared, because that's what's in there, and then times the derivative of the inside, which is 1/2 t to the negative 1/2, and I'll just tidy that all up a little bit. I get 1 over 2 root t, and then the bracket says 1 plus t. Oh, but that's not what they wanted. That's v at t. They wanted v at 16, so I sub into 16 here, and I get 1 over 2 root 16 times 17. V at 16, I get 1 over 136 when I sub that in there. Okay, here's another one. Derivative of secant inverse. And the derivative of secant inverse is that crazy absolute value one. So I get 1 over, okay, what was it? Absolute value of x, but here it's absolute value of 5x to the 4th. Then it was square root x squared minus 1, but here it's going to be 5x to the 4th squared minus 1. Then times the derivative of the inside, 20x cubed. So let me just tidy that up a little bit. 20x cubed over absolute value of 5x to the 4th. And the inside here is going to be, what, 25x to the 8th minus 1. But nicely here, 5x to the 4th is always positive. This has an absolute value symbol around it, and that came from the idea that we wanted this answer to definitely come out to be positive. But 5x to the 4th will always be positive anyway, so I don't have to worry about that. I don't need the absolute value bars. So when I take away the absolute value bars and then do some cancellation there, I get 4 over x root 25, x to the 8th minus 1. Okay, that's done. Last one, find the equation of the tangent of cotan inverse. Now I look up my cotan inverse derivative and I see it's negative 1 over x squared. Nice easy derivative here, dy by dx equals negative 1 over 1 plus x squared. And so at x equals negative 1, dy by dx is negative 1 over 1 plus negative 1 squared, negative 1/2. So that's my slope. So therefore, y equals negative 1/2 x plus b. That's my equation of the tangent. Now I need an xy pair to sub in. Well, okay, that's going to be a little bit difficult. To get my y value, I need cotan inverse of negative 1. And to find cotan inverse of negative 1, well, okay, negative 1's not too bad. You could do cotan inverse of -1 by drawing the picture and doing your special triangles and so on. You definitely could do that. But if you wanted to use your calculator, I wanted to show you how to use your calculator for this. You'd have to use your calculator identity from up here. That is, it says if you want to find cotan inverse, you've got to do pi over 2 minus tan inverse. You switch that over to pi over 2 minus tan inverse. And when you punch that in your calculator, you get pi over 2 minus negative pi over 4, and I get 3 pi over 4. Very good. So now I've got my xy pair to sub in. Sub in -1 comma 3 pi over 4. And so I get 3 pi over 4 equals 1/2 plus b. And so 3 pi over 4 minus 1/2 equals b. So therefore, equation of tangent is y equals -1/2 x plus 3 pi over 4 minus 1/2. Keeping it all nicely exact there. All right. Okay, so don't let this stuff overwhelm you. It really is very nice once you practice it a little bit. It's a little foreign, but some of the tricks are very repetitive, and you saw those tricks go through there. And if you're having trouble, please just rewatch the video and go back on those times I said to try them on your own. You do try them on your own to build those skills. Okay? Have a great day.